I studied drug resistance so that we can prevent cancer from taking people that we love too soon. Because cancer is common and deadly, most of us have lost someone that we would have dearly loved to spend more time with. For me, that person is my grandfather, Ed. As a child, I didn't like to drink milk. And I have powerful memories of how my grandfather would encourage me by offering a glass of milk with a plate of cookies. He would sit and talk with me while I ate all the cookies and took a single sip of milk. And he never got upset. Day after day, he would try again and again to get me to drink more milk. When I learned that he had cancer, I was scared. And I was shocked when he died a short time later. I know many of us can relate. Losing my grandfather motivated me to understand drug resistance and cancer so that all of us can have more time with the people we love. Anti-cancer drugs are powerful tools that can give us more time, but drug resistance often renders these powerful drugs useless. Cancer cells tend to divide rapidly and make imperfect copies of themselves, which fuels the development of drug resistance. Anti-cancer drugs often kill the majority of cancer cells, but if a small number of the imperfect copies can figure out how to outsmart the cancer drugs, they will multiply. And the cancer that comes back cannot be effectively treated. While we have made tremendous progress in treating cancer, drug resistance remains a largely unmet challenge. Drug resistance is complex and difficult to analyze. The number of possible mutations is almost limitless. A single cancer gene could mutate in hundreds of thousands of different ways. We wondered, could there be a way to predict or find mutations that cause drug resistance earlier in the process? Maybe even while new drugs are being developed. Maybe even before they have a chance to develop resistance in patients. It would be a nearly impossible task. You'd have to generate all of those hundreds of thousands of possible mutations and then test each one individually against multiple potential drugs. That nearly impossible path forward is exactly the one my lab pursued. We have pioneered strategies that enable us to comprehensively analyze all possible mutations in a gene that could lead to drug resistance in a single experiment. The key innovations were generating comprehensive libraries of all mutations and using high-throughput DNA sequencing to track each possible variant. Using this approach, we can rapidly and comprehensively determine how hundreds of drugs impact drug resistance. This gives us a tool that we can use early in drug development to identify the potential drugs with the lowest chance of developing drug resistance. My lab has successfully used this approach to assess drug resistance in leukemia, driven by the BCR-ABL1 oncogene, and in melanoma, driven by the BRAF V600E oncogene. To accelerate this work, our goal is to incorporate it into drug development processes in collaboration and partnerships with biotech companies. I believe this approach has the potential to transform the development of more effective anti-cancer drugs that can give all of us more time with the people in our lives who we love the most.